All right, guys, so to move on, we need to look at 2.27. 2.2.7, the maximum number of infected individuals. So can you see now that this is part of a review of a disease? After you create your model, when there is an outbreak, then you start reviewing. Even after the pandemic, you can start reviewing and say, look, we think that the epidemic, you will say, look, we think that the maximum number of infected individual was this much, and you try to tally things maybe with the intervention processes that you did. Maybe you administered vaccines. So if you administered vaccines, you can actually account for the vaccines that you administered. You can actually account for the beds in the hospitals. So this is part of public health policy. So you need to know the maximum number of infected based on the model that you proposed. So in this particular case, we have got a situation whereby Howard actually said, look, to show we cannot explicitly solve the SIR system of the more ODEs. That is very, very difficult to do. Like when we say explicitly solve, we mean that if you are given a differential equation, then you can actually come up with a solution. Say the y, the x is equals to yx like this. You can actually solve this differential equation by separating variables, isn't it? dy over y is equals to x dx, and then you integrate both sides, and then you can, so this is explicitly solving. All right, explicitly solving, but we can't do that with this system of three nonlinear differential equations. But what we can do is to give some sort of analysis. And the first thing that we want to do now is to say, look, given that ds dt is equals to minus beta si, and we also have got di dt, which is equals to beta si minus vi, all right, something like this. So in other words, I can be made can be factored out, then we've got beta s minus v, like that, right? These are the equation 1 and equation 2. So we want to divide equation 1 by equation 2, like that. All right, so the dt's are going to cancel, and you are going to remain with ds di is equals to equation 1 divided by equation 2 I beta s minus v, like this, and then the i's will definitely cancel like that. And then if that happens, then you now have this guy. What is this guy? You now have a differential equation that you can solve explicitly. You are now solving s and expressing the answer in terms of I, or you can also solve for I and express the answer in terms of s. That's what we are doing here. So if we do this, so what do we have? What we have is ds di is equals to, I didn't want to do this. I didn't really want to dwell on this guy minus v, like that. And to solve this, you can see that you can separate variables and take the I to this side and everything with s to that side. So you've got ds and then minus beta s over beta s minus v minus nu is equals to di standing alone, like that. So you integrate both sides, and what answer are you going to get? Well, this is the same as minus beta over minus beta s over beta s minus v ds is equals to, well, when it comes to this side, honestly speaking, because this is a constant 1, you are simply going to get I, right? So you are simply going to get I, but on the other side now, that's where there is a little bit of some drama. Oh yeah, because I think this guy was supposed to come on top when you divide, because we have got ds dt, which is this guy, divided by di dt, which is this guy. And then what you then do is you end up having dt di when you multiply, and it means that this becomes the numerator and this becomes the denominator, which makes our life much more easier here. So we've got, let me just fix here. So we've got beta s minus v over minus beta s, like that. And each one can be written now in terms of the denominator, beta s over minus beta s minus v over minus beta s, like that, and then ds. This will help some people because now you can do that and get a minus 1. Then you remain with this guy, but minus v over b is simply a constant, so you have got the natural log there. So in other words, you will get minus s plus ln, it will be ln s, right? Minus s plus ln s, but then there must be a v over b there, like that. Okay, so that is the sort of thing that you get, minus s plus v over b ln or log s is equals to c, because obviously this is the indefinite integral, so you must get an integration constant, so you get is equals to c. And if you look at this now, this will tell us that for t is greater than or equal to 0, it, that is provided obviously that you are going to take now this guy to that side, this guy to that side, this one becomes negative as it is here. And for initial values, you are going to be having I0 and S0 V over B log S0. So we are simply saying at t time is equals to 0. That's what you have got there. Now, one of the things that, so I did this calculation for you, and it's an easy exercise to show that for initially fully susceptible populations, you are going to get that your Imax, because our Imax comes from the fact that whenever we have a steady state, where do steady states okay? We said steady states okay where, let me use S dot here, is equals to 0, I dot is equals to 0, and R dot is equals to 0. This is where we get our steady states. So when I dot is equals to 0, that's where we get our maximum number of infections, all right? And why is that? It is because, remember, infections, they increase and then stop increasing, then they start decreasing, all right? So here, where they stop increasing, at the turning point, that's where our maximum is found. So at the turning point, the gradient or the rate of change is supposed to be equal to 0. And then from there, but how does that happen? We said I dot is equals to positive beta Si minus Vi. And we said this equals to 0. And we said actually we can factor out our I, and if we factor out our I, we get I beta S minus V is equals to 0. So when I is equals to 0, all right, when there are no infections at all, or when S is equals to, from this one inside here, when S is equals to V over beta. So that's what they are saying here, to say, look, when S is equals to V over beta, so we have said when I is equals to 0, or when beta S minus V is equals to 0. That's when we get our Imax. So for the case where I is equals to 0, we are going to ignore it. We are going to focus on the case where S is equals to V over B. And in other words, that's where we are coming. We are going to come and say, look, from the solution that we found it here. We can actually write V over B there, and V over B there, and V over B, where else can we write V over B? So where S is equals to V over B. All right. And that is the case that we are now seeing being demonstrated over there. All right. And then now you can also show that when it is fully susceptible, it means that when S0 is equals to N, you might want also to do this exercise and show that Imax is equals to this guy that we've got there. So of interest on the work that was done by Howard are the plots again. Because what they then did is they said, look, what is the relationship between, if we are to plot what is going on between, if we've got the susceptibles, as the number of susceptibles is changing, what is happening to I? So you find that we are going to pin S, the number of susceptible maybe to this, just to this one value that we've got there. And change the various values of the number of infected, the initial number of infected, and see what is going to happen. But what we are supposed to expect is some behavior that goes up, and then we start seeing stuff going down like that. That's the kind of behavior that is we are supposed to witness here, and we are going to talk about that in a plot, and we do the plot in Python in the next video. So what was this all about? This was all about finding the maximum number of infected individuals that we were having, and that is important for control mechanisms, to design better control mechanisms in the event of the next outbreak.